Okay, so now that we have done a reasonably elaborate introduction, right, spanning over a few lectures, it is time that we jump into the topics. But before, as I warned earlier, we will not right away jump into a specific modality. But before we do that, we need to orient ourselves, actually do some quick review of some concepts, and recall that we said each of the modality that we will cover can be actually treated as a separate module. So after the introduction, right, I said you could actually go take a particular modality and then complete that as well, right? It will be self-contained. But before we do that, this part of going over the tools, the concept of how we are going to organize each of the different medical imaging system in the same format, right? We talked about physics, instrumentation, and then recon. So here we're going to quickly review how we see the imaging system from a signals and systems point of view, which kind of forces us to kind of brush up. I'm using the term brush up because signals and systems you would have encountered by this time if you're in any typical engineering program, right? You would have encountered signals and systems at third semester, fifth semester, second semester, depending on which institute you're attending. So the point is you probably know, but then if you already know, if it is such a basic material, why even do a review, right? You're supposed to review it by yourself. But that is not the case, because although we are going to talk about images, so there is an additional dimension that is coming into picture. Even though mathematically it may seem straightforward, I think it could do you good to get a feel for it again, and I will try to prod and make you stretch your understanding of your 1D to 2D. Okay, so this is in that context going to be a review. That means I'm not going to jump in and do all the proofs and state the theorems like we do in the signals and systems when we introduce the topic. So that part I leave it to you, that you should be able to go over. Okay, so how do we start, right? So what is that overview, right? What is it that I'm telling about having a template, right? Having a structure to our discussion. Here we'll central to our discussion is going to be medical imaging systems, I said. So it's the imaging system that is central. And let's get the easy ones out. What do you expect the imaging system to do? It is going to give you an output, right? Which typically we know as the output image is what we call. This much is straightforward, at least without much. The moment you thought about the course title, right? Medical imaging system, biomedical imaging systems, this is something that you would have made up your mind. I've seen these scanners, so these are the medical imaging system, I know the output images. That much is fine, but our interest is not merely taking the output image and doing some processing or saying, okay, if this is the scanner, this is the output image you are going to get. That is not our objective. We want to understand the system, right? In the context of, okay, I get this image, but what does this image mean, right? In the context of what is going into the system. So you have an input side. So you have an input. So we are going to treat the imaging system as something that takes input of some parameters. Remember, that's the point that we were trying to articulate in the introduction as well. What is it that you want to see inside the body, right? Some parameter. So that has meaning, that has a physical sense, that is related to underlying biological process, right? So we have spatial distribution of underlying or inherent signal. So that is the signal that we are talking. So It is not X-ray, or it is not, you know, ultrasound pulse. What is the input? Think about, I said 3D object. Let's be little more courteous. So it's not 3D object, we are talking about human beings. So what do we mean by spatial distribution of underlying or inherent signal? That means, right, I'm sitting here, I'm human being. So if you take your camera as an imaging system, the output of which is what probably you are seeing on the screen, right? So the idea is, I'm a source, I'm a 3D distribution of how light is, the ability to reflect certain color of visible spectrum, right? So maybe here the color of the shirt, that is sending out some color which comes out as send out a wavelength that is corresponding to pink, right? Or my hair, right, that is, you have black and no brown skin, so you have the wavelengths that come out that capture. But notice all of this, it's surface, so you are perceiving it. Your vision is the imaging system, right, in for interpretation purpose. So you are seeing me on the screen, and that goes into your eyes and you perceive me, right? But we are interested in imaging system, right? Not the human imaging system, not the eye vision and stuff. We are interested in the imaging system, how close it captures. So this is, output is nothing but a estimate of the input. So if you are seeing me on screen, that is an estimate of how I would look in live. So this camera system is capturing me, so I am the input, output is what you see. So the output should be as close as possible to input, right? So in the context of medical imaging system, right, what is going to be your input? It depends on, we have multi parameters, right? So I'm not what you perceive right now, who I am on the screen. So if it is a ultrasound imaging system, because you are perceiving me through your vision system, which can take inputs in the visible range. Whereas the if it is an, you know, CT, it is an X-ray based imaging system, it is going to look at me as, what is it going to look at me? Oh, I am just a 3D distribution of the material's attenuation coefficient. How much can it attenuate the X-ray energy that is coming in? That ability, that is the property, that is what I am, a distribution of that. So if X-ray system, right, X-ray imaging system, imaging system that uses X-ray to probe the tissue, that is going to look at me as a 3D distribution of a material whose attenuation coefficient is going to determine how the imaging system is going to perceive me, right? If it is going to be ultrasound imaging system, it is going to look at me as a distribution of acoustic interferences, right? Acoustic scatterers, like we talked about mountains, right, giving echoes. So that is going to just see me as a water body with several interfaces that can reflect the sound back. If it is going to be an MRI system, it is going to look at me as, of the other things, it is going to just look at me as a water body. I have hydrogen, H2O. So it is going to just look at what is the density of hydrogen, right, that is distributed across my body. So it's not going to see me as a skin or the color that you are seeing me, right? That is optical property. Whereas it is going to see me as the MRI is going to see me as a 3D of hydrogen atoms, right, proton. So what is the density is going to determine how the imaging system, MRI, is going to capture me. Of course, the output there should be, or better be, related, right, closely resemble the underlying thing, because you are going to make a diagnosis or whatever based on the output image. So you're going to say, oh, there is a lot of density here, that is abnormal. So it better correlate with actual 3D distribution at that location. There, if there is some abnormality, the output estimate should correspond to the input, right? So it's very intricate, so you cannot comment, right? If you, I shouldn't say you cannot comment, if you have to make a very good use of the output image, or you want the doctors to be really making very reliable diagnosis or whatever based on the output image, this output image should be as close as possible, because this is an estimate possible to the underlying ground truth. So object of our imaging system is to faithfully do whatever, faithfully get an estimate that is corresponding to the underlying ground truth. So what we will do now, this is the big picture. So we need to quickly run through what is signal, what is system, are there some signals, interesting signals of interest that irrespective of the modality we need to brush up, like mathematical concepts. So we will start doing that. So first we will start with the signals review, and then we will go to systems. Okay, so in that case, let's move on. Signals. So what comes to your mind when you say signal? So this is something that given that I told this is going to be a kind of a review, I would like for you to think loud when you watch the lecture. Just don't wait for listening to the lecture, right? I want you to spend that time, think about what you know already. So when we say signals, what comes to your mind, right? What is it that what rings a bell? What is a signal? Oh, it's nothing but a mathematical function of one or more independent variables, and somehow that signal is going to can be used as a it's a mathematical form, right? So it's kind of a model that better have some is better represent or model or correspond or capture something physical, right? That's when it becomes interesting. So signal is a mathematical function of one or more independent variables. Having said that, if that is a broad concept that comes to mind, so what are the different categories that we can broadly classify these three signals, right? So again, you probably know it, so I just encourage you to think before I say. So three categories, what could it be? Think. We have seen maybe something is continuous. What is continuous? Signal is continuous. What does he mean by continuous? Why is he asking this question? What is continuous? Okay, I think you got the point. Idea is, if you have continuous, that means it's a function. We defined already the signal, right? It is nothing but a function of a independent variables at range over a continuum of values. That is the key. So you have the independent variable, right? It is a f of t, or so typically I'm using one dimensional. If you are done most of the physical variable that you would have used is time, right? So you would have seen about s of t or x of t, or that is something that t is what usually you start when we do 1D, especially in a course like signals and systems. So I think you are familiar with that. So the t is a continuum, right? That is what it means by continuous function. However, in our case, what are we interested in? 1D, I mean, even though mathematically it can be any one independent variable, you are probably more comfortable with time as your variable, right? So now we are interested in 2D signals or 3D signals, right? So let's take 2D signals. What do we mean by that? That means you have a function that is having two independent variables, okay, and those are continuous, or they range over a continuum. So in our case, what is the thing that comes to your mind? So quickly recall some of the introduction we did on different modalities, right? What you will notice is, say for example, if you take X-ray, right, just radiography. So what are the axes? The one that easily comes to your mind. Oh, I am a distribution of mu, right, attenuation coefficient to X-ray, and I have a length, height, width. So my variables are in length dimension and it is continuous, right? So I could say that, oh, the chest X-ray that we did, in there you see that we have the f of x comma y, right? We typically write function in terms of its variables. So in one dimension we typically write x of t or y of t, saying t is your time. But here what we covered already, x and y axis, which are spatial, right, which are in length scales. So f of x comma y, this x and y, right, are the length scale. So that is a continuous variable. So you will start to see that inherently most things, right, which is having physical, which is capturing the physical world, is going to be continuous. So like how time we use for one dimension, so space is also going to be continuous. So that much is straightforward. So next is discrete. So then you will quickly wonder, oh, now that you told what is continuous, we know what is discrete, right? We have, it ranges over discrete values. So immediately what we think of is, from probably our one dimensional background, oh, I know, he's talking about, instead of s of t or x of t, we know it is s of discretized n delta t. So at different locations it is there. So he's talking about analog to digital conversion. After that we get discretized. So the t is now discrete at delta t time, right? Fine, that is artificially done, because in live you have, physically you have continuous variable if you say t is continuum, but you are making the measurements at discrete interval, so that is fine. But here so the concept is similar, right? So instead of doing it on one axis, if you do it in two axes, then that is discrete. That much is fine. But what we want to relate to is, within the context of imaging system, can you think of something from what we have covered so far, something where you expect the underlying signal also to be at discrete or at discretized, or take a range of discrete values? Probably we mentioned this, the concept of radioactivity. I mean, right, we said in nuclear medicine. So I said you take some radio tracer and it is decaying, right? So the radio tracer is, when it is decaying, you count how many photons, gamma photons come out, and then you say that's the radioactivity, and that is dependent on the wherever the physiology, right, wherever activity takes place, you can have the radio tracer go there. So the concentration will tell you that is high activity or a low activity. I think I did really mention it. So in that context, if you recall, we maybe at high school physics or something, you would have, when you have radioactivity, you are talking about some concept called decay, half-life, right? So you see, half-life is discrete. Every half-life is when the radioactivity takes place. So that is something that is inherently discrete in nature. Okay, so with respect to 2D, yes, your concept of extending 1D to 2D of discretizing the axis is fine. I mean, that is fine, but there are signals of interest which are inherently discrete in nature. Okay. So the third category could be, well, you have continuous, you have discrete. What could be the third one? A combination of both, right? So from a explanation point of view, it is just merely completing, right? I have continuous, I have discrete, so I can have a combination of these two, right? Functions. So you have some variables that are continuous, some that are discrete. Okay, is it just completing for the sake of completeness, or can you think about a scenario or the signals that you're going to deal with the imaging systems where you would probably encounter this? So again, I'm not asking you to jump into the details because that is what we will do later, but just from introduction, because you have seen different images, I have introduced certain terminologies, right? Just based on that, you should try to really challenge yourself to see, can I find some examples from what he has taught earlier, what he has discussed earlier, what he has shown earlier. So yes, so mixed means definition wise it's fine, some is continuous, some is discrete, but a vivid example that you will end up dealing, right, is going to be, for example, compute X-ray CT, right? We used that. In fact, I remember we covered projection, we covered tomography, right? Go look back those areas, you will realize that what is the idea in tomography? Oh, I take projections from different views, right? Remember, I was using the cell phone, saying one is width, one is height, depends on the orientation. And in tomography, you get collection of different projections from different views, and then you recompute and get the 3D slice, right? That is what we talked about. So now, did you get the clue? Oh, one is projection is going to be length scale. Remember, we said, okay, I drew a circle, and I said if you project, you are going to get a line. Length scale, right? So you're going to do this. I think I drew some eyes like this. So what happens if this is one view, right? This is a projection of the circle here. What happens if I view from here, right? Oh, whatever angle that is. So there also I'm going to get a line, right? A circular disc, if you see, you project, you're going to get a line. You're not going to see the change of line from front to back. Okay, so now you get the idea. The length scale is going to be, it's a continuous. You may choose to pick values wherever, but this variable, whatever you're going to measure, this is the signal, if I'm going to measure the signal and mathematically write it, I'm going to call this, say, sum f of L, right, comma, I have to have some coordinates defined, so that if this is 0 degree, this is some other degree, so I can have some theta, so I can have a reference coordinate, so I could still do a regular coordinate system and say, oh, this is 0 degree when I view from here. When I view from there, maybe I'm moving 30 degree clockwise, right? So I could have some theta. So I can represent the collection of these projections, right? That is my signal, as a combination of a continuous variable and discrete variable. Because I am picking, right? I am picking locations, I am getting views. I can have fine stepping or not, but the point is you are collecting from different views, finite number of different views inherently. So your signal that you obtain is going to be a combination of continuous and discrete. Of course, then you use this signal, process this signal, create an image. Okay, so that is something of interest. So now, of course, I just was excited and I wrote on top of this. Never mind, you should be able to see. What we want to do is, okay, having talked about signals and having talked about f of xy, right? We are just going to call it as f of x comma y, a function that has two independent variables. X and y represents the two spatial directions. So now the question is, if I have this, how do I represent it, right? How do I visualize this? Okay, so simple things. Again, 1D you probably know, right? I mean, you should know. For example, let's take any simple function, one dimension, and see if you plot it, right? How do you represent it or visualize it? So just for sake of continuity, right, before we get into the 2D f of x comma y, if I tell that you have f of x is equal to sine x, right? This is a function, this is a signal. So how do you represent it? How do you visualize it? You will be able to quickly do. This is no brainer, right? I will have the axis, I will plot x, I will have magnitude there, so I'll do, it's not, okay, right? You're going to, so sine 0 is 0, so you're going to have maximum of 1, and then it's going to go to minus 1. So you'll be able to visualize, right? But then notice, I mean, this is kind of a I know it's a overbeat, but then this is one dimensional. But in order to visualize this, what did I do? I've used the plane of the screen, right? But plane of the screen is 2 dimensions. Why? Oh, because when we defined one dimension, we said it is one independent variable and that forms one axis. That forms one axis. But then the value forms the other axis. So when you have one independent variable, I am using another dimension, so for visualization or representation. So this becomes, I need a plane 2D to represent or visualize. So that means going forward, if I have f of x comma y, what would you expect? How do you represent? How do you visualize? What do you think? Okay, if we paid attention to this part, then quickly we'll recall, oh, that means f of x comma y better have x and y as 2 axes, right? And then you have to have a third dimension for the values. Clear? So now f of x comma y, if I want to visualize or represent, straightforward extension of our understanding of 1D representation leads us to something like this, where you have x axis, y axis, clear? X axis, y axis, and a third axis. You can see the valleys and peaks here. So if you were to take some cut here, for example, now this cut is going to be a 1D signal, right? It is going to be f of y comma at x is equal to some value x1. So this is not varying. So this is going to be a 1D variable. So if I take that, then I know how to plot it, right? This will be my y. This will be my y. So you're going to have value. So if this is 0, for example, just for, right, this is, if that is 0, right, this is 0. So if I start, it's going to have some black is 0, for example, then I'm going to go up, then a lot of fluctuations, then there is, when I get to there, I see black, it goes to 0, and there's a lot of fluctuation. So this is a signal. So it's a 1D signal. I'm able to plot it. This is fine. We know. So like this, you have done, right, what you visualize, f of x comma y, you get this. So this is actually very important to get this insight, because if you're going to get the raw, you get the data and then you have to do the image reconstruction. What if you want to do image processing, right? Basically, if you go into your workspace, right, if you're reading the variable f of x comma y, this is what you will see. This is how it is. So you can get a feel for how the signal is varying. However, if you show this for the end user, say you show this to a radiologist, he will just say, what is this? This is not a typical image I see. So he's going to use the term image. So you have been very correct in your representation. You have done f of xy, you have actually plotted it. But in imaging systems, the output we are expecting to be an image. So how do we do that? Because looking at this, you cannot, I mean, when I reveal the image, you will see why this what you see here as a signal looks weird to the doctor. Okay. So then how do you represent? How do you visualize? Oh, we don't worry about plotting. We use what is called as pixel element. Sorry, picture element. That is your pixel, right? So we convert this into an image. What we do is, the third dimension, we color code. Let the maximum value be white, minimum value be black, right? You can have different schemes of mapping this, but so you essentially encode the third dimension, encode as in color code. If you do that, you still use x and y. The third dimension that was coming out, right, when you plotted, instead of that, we converted that to a color representation. So if you do that, this is what you see. It's the same f of x comma y, it's the same signal. It is just that you are visualizing this by color coding the third axis. So now you get the point. So if it is one dimensional signal, you needed 2 dimensions to show the plot, how the signal is varying. So if it is going to be 2 dimensions, then you need 3 dimensions. So you can imagine, if you have a 3-dimensional variable, 3-dimensional signal, how would you visualize that? Okay, so that's a thought exercise. I mean, you can do that. So now you get that image is not a big deal, x comma y, and the third color, that much is followable, right? But this is something that you will appreciate. Oh, we have seen these are brain scan. If you and I can appreciate that, clearly the clinical practitioner is going to be very comfortable only with this. He is not going to look at this and say, oh, you are mathematically correct, it's same f of x comma y. But he's not going to make a diagnosis based on that. Clear? So this is fairly straightforward, but I wanted to spend this time because based on my experience, I noticed that the small stretch of imagination, if you don't appreciate, then all the reconstruction and all the things that whenever you use f of x comma y, there is no feel, there is no intuition, there is no appreciation for how this is happening. So it becomes just a mathematical exercise. But if you spend this extra 5-10 minutes understanding this, which is probably not complicated, but I found this to be helpful from the student feedback. Okay, so much for the signal. Then what do we have? So we call what is called as picture element. So if this is a picture, you have picture element, that is your pixels. Okay, so after that I won't say anything because you all know what is pixel and how many pixels is good, how many pixels is not good for your application. You know that. So it has relationship to the image quality, so that we will cover little later. Okay, fine. So f of x comma y, so for 1D we know 2D. Just for extension we need to work also for 3D. Okay, and the reason for that is some of the modalities that we will cover, inherently you will have, I'm going to cover the whole volume. So can I just do a slice? So even this slice, if you look at it, this is saying that this is infinitesimally thin, right? Everything is on plane of paper. You don't have the z direction, x and y. Z is, there is no delta z, there is no width. That's what it's mapped to. But in reality we are 3D, so there is going to be width. So what we will encounter is not picture element, we will encounter volume element. So when I say volume element, you will probably not recognize, but if I say volume element is abbreviated as voxel, then you might probably start to relate, right? You've seen voxel and the MRI, for example, right? There you start to talk about voxels, because it's all volume elements that you're going to play with. So that means this is a 3D object. I have a 2D slice, which is going to be my image. So this is your pixel. So when you have a height, right, or slice thickness to it, then it becomes a volume. A surface area times height or depth is going to be a volume. Okay, so we are going to call this now as voxel, and several of these slices, if you stack, then you can cover the 3D. So we will use volume elements when we are doing 3D, and when you are doing imaging, typically, even though it's the same value within this thickness, you are going to project this on plane of paper. That means you are saying you are collapsing the depth information. You are projecting on plane of paper, so it becomes a 2D. So we call it image, and it's called picture element, pixel. Okay, so let us quickly move on. So we now got a hang of what signal means and how we represent or visualize two-dimensional signals, and of course three-dimensional signals as well right here. So now it is in order for us to proceed quickly to revise, refresh ourselves on some typical signals of interest that you will encounter several times. Okay, so what are the specific signals that we are going to encounter here? We are going to talk about point impulse, comb and sampling function, line impulse, and few other functions like rect and sync. Of course, relationship between exponential and sinusoidal signals. I mean, this is just scratching the surface. The idea is these are all unique. These by covering these, we should be able to address 99% of the introductory material that we have. However, if you are going to work on any particular signal processing aspect more, perhaps you are advised to explore this further, right? But that is not intended for this course, for this audience. So similarly, we'll run through. You have 1D, right? One-dimensional signal. I already plotted a sinusoid, so you know what it looks. So if you have point impulse, right? What is 1D point impulse? Have you seen point impulse when you covered 1D? No. What do we mean by that? I mean, we probably have heard impulse, right? So you, at the origin, you would have seen something like this: a delta function, direct delta, impulse function. You would have heard that. What is point impulse? Same concept. Instead of 1D here, right? So for example, this was 1D. At t equal to 0, you have everything packed. So that is your impulse, direct delta, whatever you want, right? So point is going to be when I have two dimensions, at the origin, right? At the origin, that is a point. So point impulse is same, right? It has all the energy at that location, zero width. Your point impulse should mean similar, just that it doesn't have anything on x or y, say x and y. So it doesn't have, all the energy is packed at the origin of x comma y. So point impulse. So we can 1D, you are familiar, you would have heard about delta function. So delta of x is 0 when x is not equal to 0. So that means everything is packed only at 0. Outside 0 you don't have any value, it's all zeros. That's its definition. So the uniqueness of this is hardly this function is used by itself, right? Mostly it gets its meaning, or the way it is way it gets utilized is delta x combines with some other function. It kind of combines. So here it is multiplied with some arbitrary function f of x. So delta x multiplied with f of x, and then the energy that is integrated over that sum, right? That comes out to be f of 0. That means the function's value, this is any function f of x, when it is combined with a delta of x, right, then you can essentially pick this f of 0. That means the function f of x, whatever value it has at 0, can be picked out, right, because of this delta function. So delta function is unique in that sense that it is not by itself, it is defined, but it's interesting because it can be used with other signals to extract, pull out the value of that arbitrary function wherever delta function exists. Okay, so that is your 1D. So you can extend the same concept to 2D as well. So that means it is defined only at origin, right, at 0, 0. By itself it doesn't, it's not utilized, but then it combines here, right, a two-dimensional signal. Instead of f of x, here it is f of x comma y, and you will notice quickly this can be used. F of x comma y means it is pulling out f of x comma y's value at 0, 0. So because delta function is defined, point impulse is defined at 0, 0, the function f of x comma y, any function f of x comma y, its value at 0, 0 can be pulled out. Wow, this is fantastic, right? Why? Because f of x comma y is a two-dimensional in space. It can have any value anywhere. What if I want to know the evaluate that f of x comma y at particular location, right? So I want to locate f of x comma y, I want to know at this location. This location is some offset from here. I know this value now, right? F of 0, 0 using the delta function and integrating it. What if I want to know a value here? I can use my delta function to pick. How do I do that? I have delta function at x comma y, right? It is like this in the space. Now if I can shift it, right? So I can shift it by some epsilon comma eta, then your delta function is shifted, right? X minus epsilon, y minus eta. So recall the definition of the point impulse. You will quickly see this operation f of x comma y is existent over the space, but my delta function is existent only when its argument is 0. That means when x minus epsilon equal to 0, or x is equal to epsilon, y is equal to eta. Only there you have delta non-zero. That means only there I can get my function, right? So that is your shifting property. So you can basically use shifted version of your delta functions to pull out values from f of x comma y at those locations, right? This is shifting property. Okay, so as we go further, I think this is all 1D equivalent. So if you had already appreciated 1D powerfulness of your delta functions, delay and whatever you're pulling, especially in the linear systems concept, this is a straightforward extension. Okay, so you can move your delta function, and then pick at f of x comma y. So the value of f of x comma y at this location can be pulled out using the shifted delta function, point impulse. Okay, so other properties like scaling or even function are straightforward extension. So if you have we had only x and y before, but if you scale the axis, right, if you do ax and by, then you will get delta of x comma y, you will get this here. So it is a scaling property. So if you scale this axis here, the value gets scaled. Okay, so this is your axis scaling, this is your amplitude. So if you change here, if you scale here, it gets divided by this value, right, so as to keep the energy constant. So the idea is, this is your scaling property. This is what is called as even function. Again, this is, you can, even though it's listed separately, this is nothing but what happens if your a and b are is equal to -1, right? A equal to b equal to -1 would essentially be delta of minus x comma minus y, which will be 1 by 1 of delta x. So it's just a derivative, right? So, but it is specific, it's called as even function. So those things are straight carry forward from your 1D signals that you probably know, nothing much. So let's quickly move to the another important idea of line impulse. Line impulse, okay, you now have the value of point impulse, right? Point impulse is very immensely useful. You will look at it from image quality perspective eventually, right? If you have an ideal point at 0, and if your imaging system is going to take, so I have an ideal point, okay, this is your ideal, and then the imaging system is going to take this point and is going to show this point, right? The objective is, your output image is an estimate of ideal input, but because of the imaging system's point, right, this is a point impulse, system's response to this, so your point spread function, you will see that this is bigger one, so there will be blurring. Okay, so it is related to resolution, blurring, image quality. So it's a very important, point impulse is an important concept, it's an important mathematical operator. So why then line impulse? Similar. So now instead of just using point, if I want to characterize the imaging system, I could use calibrated way to do it, and it might be beneficial. Some say, instead of making a point, if you have to make a 3D object, that means I'm going to talk about a sphere. Instead of making a very small sphere, right, infinitesimally small sphere, and placing it and trying to image, which may be challenging, it might be easier to have line targets, a wire with different dimensions. So in calibrations, line targets become very useful, and therefore to mathematically represent that, we need to have line impulses. So first we write, right, you can have line impulse. What does it mean? Oh, that means I have a delta function that exists only along the line, that is non-zero only along the line. So I have delta of, here L is equal to x cos theta plus y sin theta. So that means, where is this line? Oh, this line is in space x comma y space, right? So it has some angle, the norm to this line from the origin makes an angle theta, and the length along the direction of the norm, right, is L. So now you can write a line in this space x comma y with different orientation and at different locations from the origin. Okay, so this is your line impulse. So immediately when you do that, you can think about different functions. So comb function. What is a comb function? You know the comb that we use. How does it look? Oh, it is usually a comb. You have a line, and then you have teeth right? That is your comb. So comb function should similarly have, that means it is mimicking that. So you have a line, but it has values, right? The spikes only at special locations. So comb of x comma y is nothing but a collection of this at different offsets from m and n, different locations m and n, right? X comma y plane at locations of m and n, you are moving this delta. Only there it is there. So if you visualize that, it will look like a comb. And again, why is this important? We already talked about using these delta functions to pick values of the continuous function. So naturally, that means you can envision if there are going to be spikes, right? Delta function here like that m comma n, then maybe I could use, and I pick off from f of x comma y, if I pick off values only at discrete locations m comma n, that means it is equivalent to sampling also. So you can view this as a sampling as well, delta of x comma y, and you are picking samples spaced delta x in the x direction, delta y in y direction, which is nothing but a collection of delta functions where x, right, it is defined, only x is defined at x minus m delta x, meaning whenever this argument goes to 0, whenever this argument goes to 0. So that means x is equal to m delta x and y is equal to n delta y. That's when you have the values that you pick. Those are the discrete locations. So that is your sampling. Okay, so that is why you will kind of use this more and more. Again, you could use the same argument. You could get these relationship between sampling function and comb function. So you can use this comb function to do sampling. So I can take the space out and I can get discrete locations, valued at discrete locations. So we will stop here and we'll continue the next lecture from this location. Thank you.